Our next speaker is Professor Igor Klebanov from Princeton University, and his talk is about confinement from Conifold and other short stories.
Okay, so I selflessly gave myself only one lecture at this school, so I hope you'll forgive me for running a little bit over time if I need to. Because compared to the title online, I added other short stories. Basically, I want to start with a little bit of an overview of what we heard so far. So we had excellent kind of broader lectures by David Gross and by Edward Witten last week. And then had a lot of lattice gauge theory. But I heard a lot of questions, nevertheless, from students, especially at dinner on Friday, like, what is the big picture here? What is this collaboration about? So, of course, this is a school that wouldn't be taking place if not for the Simons confinement collaboration. So I'll talk a little bit about that. So of course, we by now know that QCD is a perfect quantum field theory. It's fundamental Lagrangian, can be put on a T-shirt, and it's UV complete. In fact, it becomes weakly coupled asymptotically. That's this famous asymptotic freedom phenomenon discovered right around 50 years ago by Gross and Wilczek in Princeton and Politzer at Harvard. And it is the part of the standard model that can stand alone. It need not be embedded in a bigger unified theory. It's perfectly happy by itself. As we heard a lot, it admits a lattice definition that matches onto the asymptotic freedom while allowing the theory to be defined non-perturbatively at long distances. And of course, the precision of that can keep improving. So what's the confinement problem? So of course, in this Lagrangian, you see it's a kind of analog of QED. And for QED, we of course have photons. So classically, there will be massless degrees of freedom, the colored gluons. Nothing gives them a mass here, but somehow they don't appear as asymptotic states. All the colored states are confined into colorless hadrons. But of course, on very short time scales, we do see propagation of colored objects. For example, if you look at some detector event, you sometimes see say a bee quark traveling some distance before it hadronizes. And so we see like the reality of quarks and gluons in these events that eventually become collimated jets. So this is an incredibly important fact for the phenomenology of particle physics. And among the Clay millennium problems that came out around the year 2000, it's the #1 problem in the list. And it's formulated in terms of a mass gap. So mass gap basically says that even though classically or semi-classically you see these massless gluons, there are no massless states in the spectrum. There are only massive bound states. And no proof of this property is known. This was the statement around 2000. There is also a more detailed technical version, and the status still says unsolved. So that's why we applied for the Simons confinement collaboration a couple years ago. And this is the crystal ball kind of symbol of our collaboration that Grisha created. Very nice image. And every group of people needs a kind of motivational quote. And actually, I added this to the slide literally yesterday, because yesterday I stumbled onto a new trailer for Oppenheimer. There are various trailers, and there is a new trailer that came out a week before the release. And I almost couldn't believe my ears when I heard the character Oppenheimer saying, it's about unleashing the strong force. And there is also a continuation of this that I won't put on this. Okay, so this is just to say that this is somehow our goals are broader than just proving confinement. There are, of course, multitude of phenomena in strong interactions, and we want to understand a lot of this stuff. Okay, so senior personnel, just to give you an idea who we are. Several of us are lecturing here. You'll see in particular on this page pretty strong overlap. And there are a number of postdocs and graduate students from the collaboration who are here. Okay, this is another another motto of the collaboration. This is actually the logo that was devised. So there are sort of three sides to the triangle: computation, phenomenology, and theory. And we're supposed to kind of use the interplay between these three. And this is a quote from another iconic film. Well, Oppenheimer is going to become iconic, that's pretty clear. This one is already quite old. I won't say what it is, you might know. A, always B, C, collaborating. And if you are on the computation side, you can replace collaborating by coding. Always be coding. All right, so part of the reason I added this introductory stuff is because of questions, somewhat pointed questions asked, posed to me by PITP students at this school. And basically it's what exactly are we supposed to be proving? And this was after, it's a very good question. So as we learned during the first week of the school, the answer depends on the model and also may depend on who you ask. But there is, I think, one thing that everyone is likely to agree on is what happens in pure glue or pure gauge theory, namely when you throw out the matter fields and just have only the gauge field part in 3+1 or 2+1 dimensions. There, the clean order parameter for confinement is the area law for the large Wilson loop. So let me just review this a tiny bit. So we have this Euclidean lattice SUN gauge theory, and the action is a sum of the plaquette terms. So for each plaquette, you have a product of fields this way, this way, this way, this way. So there are two U's and two U daggers. One thing, so this was devised by Wilson around 1974, and this action is extremely friendly for doing strong coupling expansion, namely just assuming G is very large, so this coefficient is small, and just expanding in these plaquette terms. Then you basically see that if there is a very large Wilson loop, you have to fill in the area by plaquettes, because the integral over the Haar measure of a single U will just give you 0. So you need to cancel this U by an opposite running by U dagger on the same link. And then you fill in this loop, and you see that in the strong coupling expansion, you immediately get area law of the Wilson loop. But of course, the strong coupling expansion breaks Lorentz invariance. The theory is not rotationally invariant, so it's just a formal trick where we're very far from the continuum limit. Right, so what we need to do, and this is why there is a lattice Monte Carlo, is to extrapolate from very large G to very small g and hope that this area law does not get erased. And in particular, you have to tune things so that in the continuum limit, one needs to interpolate to the weak coupling on the lattice scale. Namely, yeah, this should be G0, really. I took it from a very old review paper by Kogat, which is still actually very useful to read. And you see, so G0 is the coupling in the Lagrangian on lattice scale. And we know that, so A0 is the actual lattice spacing. As you increase the lattice spacing, this G is going to grow. And as you know, so in this approximation, it grows. So if you plot 1 over G squared, it's going to hit 0. It looks like a straight line versus the log. It's going to hit 0. And the place where it hits 0, what is that scale called? Exactly, it's lambda QCD. So that's like the main thing that we learn from this one loop running. Of course, the one loop running comes from this famous beta function whose 50 years we're celebrating now. This is B naught that was just reviewed. So we have B naught is 11/3 n minus 2/3 NF. And the main thing is that there is a minus sign here. So as Xiaomi just discussed, when NF is smaller than 11 halves, n, then the theory is asymptotically free. So we need to send the lattice spacing. So you have to take kind of this double scaling limit, or triply scaling limit. You send the lattice spacing to 0, you send the number of lattice points to infinity, keeping the size of this, let's say we're on a 4 torus, so we're keeping the torus size fixed, and then we simultaneously send G naught in the lattice section to 0. And in that limit, what should happen is right around the place where the one loop coupling running diverges, we should instead get a nice regulated theory with an emergent scale. And this, I think Sidney Coleman named it dimensional transmutation. So this lambda QCD emerges, and this is a finite quantity because A naught goes to 0, but 1 over A naught diverges, and this goes to 0 so that they balance out. And what should happen is that the bound state masses and the square root of the string tension, namely the coefficient. So the string tension is just the coefficient of the area law in the Wilson loop. They should be just pure numbers times this quantity, lambda QCD. So that's what we're supposed to prove. There is absolutely no doubt. One has numerical evidence for this. By definition, from numerics, you cannot exactly approach the scaling limit. So this is so even the early calculations of Wilson, and in particular by Kreutz, already showed evidence for this linear growth of the quark-anti-quark potential. This is from a plot. Beta is 1 over g squared, and you see that it hasn't really, we haven't reached any kind of limit here, but you already see the linear potential. So proving this asymptotic linearity is sort of one of the goals. If someone manages to accomplish this, this would be certainly a big breakthrough. But then there are, of course, many other gauge theories. And for example, if you take the theory with massless quarks, then there is really no mass gap, right? Nor is there a strict confinement criterion. So one has to think harder what we're supposed to be proving. But this exponential hierarchy between the UV cutoff and the infrared scale is a kind of signature of this non-abelian gauge theory. And this is what the confining flux tube looks like in these simulations. You stretch quark and anti-quark, and you see a flux tube whose diameter is right around the Fermi, and it doesn't change much it only changes very slowly, logarithmically, as you change the distance between quark and anti-quark. And when they're far apart, the small fluctuations are described by the Nambu-Goto area action with corrections that are notable, and Sergei Dubovsky will talk about these string effective actions. So there is considerable numerical evidence for formation of these flux tubes, but no proof, alas, no analytic proof. So one of the best evidences for string theory that there is the so-called Regge trajectory, linearity of the Regge trajectory. This existed long before QCD, and this is a plot of J versus M squared for states of isospin 1. So it starts with rho meson and goes like this. So the leading Regge trajectory is sort of the unexcited spinning string. And you see that the tension, the energy density of the string is in about 1 GeV per Fermi. Fermi is like the typical distance scale for strong interactions, and GeV is the typical energy scale for strong interactions. Okay, so this is just the basic stuff. And now I will talk, now there will be a few short stories. Basically, some of them will be fairly old, some of them pretty recent. But I think what we're aiming for is some solvable models or models under analytic control which show confinement or transition between screening and confinement and so on. And in particular, we're very interested in this exponential separation between the infrared scale and the UV cutoff. Okay, so this is so schwinger model. We heard a nice review of the schwinger model from Grisha's talk. Initially, it was just QED in 1 + 1 dimension coupled to one Dirac fermion of charge G and mass M, but one can extend it to multiple Dirac fermions. It also, as discussed already, admits a theta angle, which is just this term epsilon mu f mu. And a beauty of this model is that the one flavor model is exactly solvable for m = 0. And it reduces just to the free massive Schwinger boson. And this came back in focus soon after QCD and was widely regarded as a nice toy model of confinement, because obviously you don't have free charges running around, you just have them. And in particular, when mass is 0, it's a very strongly coupled limit, and you have tightly bound electron-positron pairs, which form this massive Schwinger boson. Its mass, as Grisha discussed, is G over square root of pi. But there are many subtleties in this model. And one flavor you already heard about, but what about the two flavor Schwinger model? So here, unlike, so for the one flavor one, you have a mass gap. Like there is just binding of these charges. But for two flavor, it turns out that there is no mass gap at m = 0. In fact, the theory flows to a conformal field theory, so-called C = 1 CFT, of a compact boson at the self-dual radius, where there is enhanced SU2 cross SU2 symmetry. So the one part of it, the SU2 is obvious, right? That's just the symmetry that rotates the two flavors of quarks. But there is additional SU2 that emerges, which is implemented by kind of the winding numbers and of this compact boson. It also has a charge conjugation symmetry, and we will particularly be interested. So there are two interesting places where this charge conjugation symmetry is unbroken. One is at theta = 0, and the other one is at theta = pi. And at theta = pi, it can be broken spontaneously, which is reminiscent of spontaneous CP breaking in QCD, which actually goes back to Dashan's work that was written even before QCD. It turns out that at theta = pi, you can just make one of the quark masses negative and do the calculation, and then this was revived more recently here. So this is from a very recent paper by Ross Dempsey, Silvio Pufu, Benjamin Sogard, and Bernardo Zahn. So it's not yet, hasn't yet passed the test of time. Actually, the paper has two citations at the moment. I doubt how many people read it. But I think it does exhibit apparently this exponential hierarchy between the UV and IR scale. I should say that, so one thing that everyone more or less understands is the limit of 0 mass. That theory has this CFT, but the CFT is coupled to a massive degree of freedom, which is a Schwinger boson. So it's not a pure, exactly solvable CFT. It's coupled to some massive stuff. And this is what Howard Georgi calls unparticle physics, this coupling of a CFT sector to a massive sector. And so in particular, it's very interesting to see what happens when you take theta = pi and move along the SU2 invariant line where the two flavors are massive, and find out what happens in particular at small mass. So let me just describe a little bit. I wish I had time to discuss bosonization, but basically one Dirac fermion can be mapped to a boson. That's a classic result. Essentially, psi left is e to the I phi left type map. If you want to hear a slogan, it's like a continuum version of the Jordan-Wigner transformation that Grisha presented in his lectures. Here you have two bosons, and there are corresponding fields phi 1 and phi 2. So there will be, and you can form two linear combinations, phi 1 minus phi 2 and phi 1 plus phi 2. And this calculation was essentially performed by Coleman in a very well-known paper in 1976. Then if you integrate out the gauge field, you make this phi plus field massive. So, and its mass is again of order G. G, just to emphasize, in 1+1 dimensions, G has the dimensions of mass. So unlike in 4D, so it's perfectly okay for a mass to be equal to charge. But there is also this massless phi minus field here, which is periodic. And for generic theta angle, the theta angle is related to the electric field at infinity. Like in Grisha's talk, he kept electric field to be 0 at infinity, but you can also introduce it, and and some things depend on it. But here you basically find that this phi minus square term, and then it's perturbed by a cosine potential times some scale. And this operator has dimension 1/2, so it's a relevant operator, and it induces RG flow to a theory with a mass gap. And the mass gap has been known since Coleman's paper to scale like m to the 2/3. So it's not an exponentially small mass gap. It's really power law small. But then you notice this remarkable fact that when theta is equal to pi, then this cosine vanishes, and then you get you basically get 0 here. So this so in particular, Howard Georgi in some recent papers asked the following intriguing question: could this theory be exactly gapless? Namely, he focused on this locus along the diagonal, and in some perturbative sense, he was wondering whether as you move along this line, at least up to some critical m, this mass doesn't render, this mass of the flavors doesn't render the theory to have a gap. And what we instead find is that there is an energy gap, but it is non-perturbatively small. So it's similar to what happens in QCD. And how do we see this? So then you can derive the following effective Lagrangian, which is actually basically comes from Coleman's paper. And this cosine term at theta equal pi, so is actually a marginal operator. And we know that marginal operators create logarithmic RG flow. And this is known as the Sine-Gordon model. It's Sine-Gordon in the sense that it has a cosine potential. But this cosine potential is marginal. So you have to consider logarithmic flow of this coupled system. There are two marginal operators. One is the d phi squared, and the other one is this cosine. And this is known as the BKT flow, or Berezinski-Kosterlitz-Thouless flow, because it's related to the XY model, which is, this is sort of one of the, actually, Kosterlitz-Thouless is, I think, one of the most important papers in statistical mechanics of the last many years. It's very well explored. And in particular, this flow was studied, and you can derive the beta functions and define the following pattern of flow lines. So this is the flow in this two-dimensional plane of alpha and delta, right? So delta is the coefficient of d phi squared, and alpha is the coefficient of cosine. And we had to find which of these flow lines is important for us, and it's actually the straight one that comes out from the unstable fixed point and goes off like this, because it's the only SU2 invariant one, and our underlying theory is SU2 invariant. And then for flow along this direction, you find an equation very similar to the famous asymptotic freedom in QCD. It has the same structure here. M is the fiducial scale. M bar is the mass at some value. And basically, this is what you get. So then you see that, again, there is an analog of lambda QCD happening here. And you expect the gap to be exponentially small, of order e to the minus a g squared over m squared. And A is, in fact, computable. OK, great. So this is the analytic argument. Just it's something that people could have done in the late 70s, early 80s, but we haven't found any reference about this. And the recent work seems to indicate that it wasn't well understood. OK, but then we also did numerical work on the lattice Hamiltonian schwinger model, which, so Grisha described its one flavor version, and here you can do the two flavor version of it. So this and you indeed see evidence for exponentially small gap emerging along this diagonal. And in fact, you can see evidence that these lines are critical. So along these lines, there is a kind of easing transition that's happening. I don't have time to talk about this. But so there are two C equal 1/2 lines that merge into C equal 1 transition right here. But along this line, you actually have evidence for the exponentially small gap, and even with the right value of the coefficient A. So I think it's a very nice test of both of this Hamiltonian lattice gauge calculation and two flavor case, also of the mass shift that we discovered in this model. The mass shift, Grisha already mentioned it, and it's particularly important in the two flavor case because at the value m alpha equals 0 here, namely if you take lattice mass to be minus nfg squared a over 8. So at this point, there is a discrete chiral symmetry in this model. The theory is exactly invariant under translation by one side. In the staggered fermion formalism, the two-side translation is the translation, but the one-side translation is a discrete subgroup of the chiral symmetry. And this model, the NF equal 2 model, actually obeys this symmetry exactly. So this shift is very important and also important in our numerical work. OK, so this is one short story. Any questions about it? I know this was a little bit fast, so feel free to ask. Yes.
Does the Gauss law depend on odds and even? So when you shift by one side, you have to.
Yeah. What happens is that because of the staggered Gauss law, because of the staggering of the Gauss law, that's why you need to make this shift up. That breaks. So if not for the staggered Gauss law, you would have m equals 0 would work. Okay, but you're essentially shifting the mass to compensate for the staggered Gauss law. Yeah, it's not obvious from the equations that I wrote, but you just have to write down the energetics of this system for m equals 0, and you see that this value of lattice masses will compensate for this non-translation invariance of the Gauss law. So this shift is particularly important at low masses. It really improves the convergence. And in fact, this model in the strong coupling limit, it actually has infinite degeneracy of the ground state at m alpha equals 0. Well, this certainly would not be the case if you didn't put in this shift. So some of the work that done in the 70s on this missed this point entirely, so actually some of the stuff really needs to be revisited. Oh, questions? Yes.
Does that come somehow from a sort of Ginsburg-Wilson relation to the Hamiltonian, or?
Yeah, unfortunately, I don't have deep enough insight into that relation to answer your question.
Wondering where does the shift come from? Because
I mean, these are not Wilson fermions. These are just staggered fermions. Everything is totally explicit here. You literally just check that that, for example, the ground state energy will be invariant under. Yeah, you can say start working in the strong coupling expansion, and then you start checking, because what happens is that if you look at what is the strong coupling ground state, it's filled only on even sides. Say the odd sides are empty and the even sides are full. So it's this checkerboard pattern, and because of the staggered nature, you have to check that, and then the mass term compensates for the staggering. All right, so let me then move on to another example, which is based on gauge gravity duality, which Silvio nicely introduced. So as you heard multiple times, there was a big breakthrough also around 1974, soon after QCD appeared, where SU3 gauge theory was extended to SUN. And Hopf showed that if you take the limit, keeping this so-called Hopf coupling lambda equal to G Young-Mills squared n fixed, in this limit, namely you scale G Young-Mills squared as 1 over n. In this limit, everything is dominated by planar diagrams. And the probability of snapping a flux tube by quark-anti-quark creation is 1 over n. So this gives you a theory with this a kind of QCD string theory with 1 over n couplings. So it's a rather opposite limit from what we had in the schwinger model. The schwinger model had the minimal number of colors, and here we take the maximal number of colors. So if you think about this picture that I showed before, yeah, this is a QCD string. If there are dynamical quarks, then they can snap this flux tube, okay, by QQ bar creation here, and this kind of 1 meson state can decay into 2 meson states. But as we heard from detailed talks on lattice gauge theory, the string breaking actually kicks in rather late. So you can still sometimes, even at finite n, talk about single string states, but still the infinite n limit is a very clean limit. Okay, and then around 25 years ago or even more, this amazing duality emerged based on the discovery of D-branes, Dirichlet branes by Polchinski in around 1995, which allowed for solution of certain supersymmetric strongly coupled theories. And I'll talk about an example of a theory which usually people talk about AD as CFT, and CFT of course means conformal field theory, so that does not have confinement. But it's possible to deform some of these dualities to create confinement and sort of solve confining theories. So how does the basic duality work? So this is a picture of a stack of D-branes. It's defined, so say here we have 4 parallel D-branes, and you can put any number on top of each other. They don't feel any force. They can be distributed as you like because of the supersymmetry, the BPS condition. And these strings are just like gluons, basically, from the point of view of the low energy gauge theory that lives on them. But then you can ask, how does the stack of branes deform space around it? So one view of it is just the open string dynamics on D-branes, which is described in the basic case by n=4 super-Yang-Mills theory. But then there is the deformed sort of curved space around it, and that is described by the following metric that Silvio already wrote down. There is a warp factor here, 1 plus L to the 4 over R to the 4. And it's like a warped product of R3, 1 along the brain and R6, which is normal to the brain. And this is a schematic picture. So in this throat limit, when you go to very small r, you basically see that this 1 over r squared from here will dominate over 1, and it will cancel the r squared here. So you'll just get L squared d omega 5 squared. So you get an S5 of radius L. And the other coordinates, as Silvio explicitly showed, combine into ADS5 of the same radius L. And when you do the matching with the D-brane theory, matching of charges, you see that the radius of the space L to the 4th power is just in string units. Alpha prime is just LS squared. In string units, it's just a 'T coupling. So if we go to very large 'T coupling, this space becomes weakly curved, and this method of studying the gauge theory becomes reliable. So this, of course, has been subject of thousands of papers since the mid-90s. And in particular, it allows us to develop a new kind of expansion. While the usual Feynman graphs develop an expansion in powers of lambda, and people have done amazing calculations on this using also exact integrability. You sometimes have control over the whole series for some quantities. But then the dual string theory on ADS5 crosses 5 allows us to develop expansion in inverse powers of lambda, in lambda to the -1/2. And sometimes these can be shown to be matching exactly. So there are pretty detailed tests of the ADS-CFT correspondence for quantities that are not protected by supersymmetry. Okay, so now this is sort of what Silvio already told us, but now are there any questions about this? I assume you heard similar talks before, but here comes one thing that people often gripe about is why should I be that interested in n=4 super-Yang-Mills theory? I mean, it's certainly a beautiful theory, but it's rather far from real world. So how can we bring it closer to real world? Well, ideally you would want a non-supersymmetric theory, but suppose you just try to break supersymmetry, say to minimal supersymmetry, n=1. And the way to accomplish this from D-brane point of view is to, instead of just putting stack of D-branes in flat space, put them at the apex of a cone. And the cone has to be a rather special cone that preserves still minimal amount of supersymmetry. It's called a Calabi-Yau space when it does. And the solution for D3 branes at the tip of the cone is practically identical to the one I wrote down. All you do is you replace the metric, the 6D metric, by you just change the metric at the base of the cone. So it's going to be basically the same solution, but this d omega 5 squared now refers to the metric on the base of the cone, and it's an Einstein metric, namely R mu nu is proportional to G mu nu. Okay, then just the matching of the volume of Y is just the volume of unit radius Einstein. It's just some pure number. So the detailed coefficients will change, but in spirit, again, when you go to G string n much larger than 1, you can again apply gauge gravity duality. Yes?
Does Y have to be a Sasaki-Einstein factor?
Yeah. I didn't want, because it's not a well-known term, but it's indeed a Sasaki-Einstein space. It has some Sasaki condition that it's basically to say that the whole cone is a Calabi-Yau space. Okay, so now let me discuss a particular example, which is in some sense, one of the most generic ones where the theory is non-trivial. Actually, the simplest examples is when you just quotient R6 by some discrete group, and they're called orbifold theories. Those were studied first. There was Lawrence Nekrasov-Vafa and Kachru-Silverstein papers, and they studied some, but those theories, you just get ADS5 cross S5 mod gamma. And if gamma obeys certain conditions, so in the bulk, it's almost the same space, but the gauge theory has usually several SUN groups and so on. But in some sense, the simplest sort of example, which is not an orbifold, is the Conifold. The Conifold is specified by the following constraint on 4 complex variables. So you take just 4 complex variables and say sum of their squares is 0. And then the base of the space is called T11 for some historic reasons. It's actually a coset space which has SO4 symmetry. The SO4 symmetry is evident because this is an SO4 symmetric equation. And one can write down the Sasaki-Einstein metric on T11. Basically, there are 5 angles. It's a 5-dimensional space. There are two spheres and then an additional circle that's bundled over these two spheres. So it's, people call it an S1 bundle over S2 cross S2. And one can show that the topology of this space is non-trivial. It doesn't just have a 5-cycle, it has a 2-cycle times a 3-cycle. So it's S2 cross S3. And this non-trivial topology allows us to do something more fancy than what we've done before, which I'll come back in a second. But first, let's just determine what is the gauge theory that sits on, say, a single D3 brane at the tip of this Conifold. So this was done in a paper I wrote with Witten right around 25 years ago. One has to solve the Conifold constraint by introducing these combinations, which we call, say, Z3 plus IZ4 equal W1 and so on. And then you know that W1, W2 is equal to W3, W4. So you can decompose them in terms of these products, AB. But then there is a quotient symmetry under, there are 2 A's and 2 B's. And you have to remove redundancy under A to lambda A and B to 1 over lambda B. And for that, you can impose this condition. So there are basically, each of these is like a 3-sphere and they're of equal radius. But then you need to gauge out one phase rotation. So if you don't follow the details of this, don't worry. It's actually described in the lecture notes that they supplied with the reading. But in a nutshell, these coordinates A1, A2, B1, and B2 become like the fields in the gauge theory. Just like in the n equal 4 super-Yang-Mills, the 6 transverse coordinates become the 6 chiral superfields. Here, the 4, these A1, A2, B1, B2 become 4 chiral superfields. And the single D3 brane has a U1 cross U1 gauge group because you need to have this gauge symmetry. The other U1 is just neutral and so on. Now, when you go to the stack of n D branes, you find SUN cross SUN gauge theory coupled to these fields A1, A2, and B1, B2, which are like matrix fields. They're in the bifundamental representation. And this is what we found is necessary is to add the quartic superpotential, which is SO4 invariant. It has this SU2 cross S. Just to remind you, SU2 cross SU2 is isomorphic to SO4. And this is a SU2 cross SU2 invariant because there are 2 epsilon symbols here. One SU2 rotates the A's and the other SU2 rotates the B's. And now you have also this global symmetry, which we call the baryonic symmetry. So basically, this gauge theory is pretty concretely described. It's of the kind that people working on non-perturbative n equal 1 gauge theory work on. And it's dual to type 2b string theory now on ADS5 cross T11. So that's by itself a pretty interesting duality. It allows for construction of baryonic objects. For example, you can take a 3-brane and wrap it over the 3-sphere inside T11 because T11 has this 3-sphere sitting inside it. You can think of this 3-sphere as just taking real z's, right? And you get a. Okay, so now this Sylvia already described, so I don't have to dwell on it. This trick for computing quark-anti-quark potential applies to this theory as well. It applies to any ADS5 cross something model, and you get the Coulombic potential. You get V of R going like -1/r times square root of lambda. So this theory is not going to be confining, right? At arbitrarily large distances, you still have a Coulombic force. All the changes at strong coupling is that lambda, you interpolate from lambda at weak coupling to square root lambda at strong coupling. But people already in the early days of gauge gravity duality understood what sort of needs to be done phenomenologically to turn the theory from conformal to confining. So this Z coordinate, you need to put in some kind of infrared wall. Namely, you need to end the space at some value of Z. And then, but the warp factor written in this form will have to be non-vanishing at this infrared wall. Then what will happen is that the string first starts out near the edge of ADS at small z, and then it sort of wants to minimize its tension. It goes to this infrared wall and stretches along here. And then you get a confining string tension, which is a squared of z max divided by 2 pi alpha prime. So that's a very schematic model. People use this model a lot for phenomenology. But by itself, it's not entirely satisfactory because you're just putting in confinement scale by hand. It's just sort of put in and does not follow from dimensional transmutation or that sort of thing. So, but it turns out that this Conifold model can be deformed in such a way that this happens dynamically. And this I worked on for several years. So it's several years worth of work that I have to squeeze into 15 minutes or something like that. But here is basically the idea. So this cone has, it's a cone over S2 cross S3 topologically. And in addition to D3 branes sitting sort of at the apex of the cone, you want to put in D5 branes, M D5 branes that are wrapped over the sphere at the tip. So maybe I'll just try to draw it. So the full arrangement is, so here is the cone, and then it has here an S2, and this is the S3. And then, so here there are still and D3 branes, and this is, and now you take D5 branes, right? So D5 branes have 2 more internal dimensions, and they can be wrapped over this S2 right here. So there will be M D5s. And then basically, very heuristically, what happens is that these M D5s want to press on this S2 and squeeze it so that it ends smoothly at 0 size. And they create magnetic flux through the 3 sphere here. So they will blow up the S3 and kind of smoothly end the S2. So you'll end up with a metric dual to this theory, which has, so this is a so-called A cycle, which is the 3 sphere. It has, so there is a particular field in the supergravity action, which is called F3. And this will be M units times the volume form of S3. And this is the crucial thing. Basically, this flux does not allow for the cycle to shrink. And surprisingly, one can write down a very simple warped. There is a very natural supersymmetric deformation of the conifold, which accomplishes this blow up of the 3-sphere. You just put in some constant here instead of 0. So you get sum of zi squared from 1 to 4 is equal to epsilon squared. Yes. So, sorry, it's just from some, yeah, ignore it. Ignore it. No, this is just from some online picture, which, yeah, irrelevant to my story. But this picture, if you remove the red part, you just have this picture where there is blown up a cycle and the S2 cycle, which shrinks to 0 size. Okay, and the metric has very similar form that we had before. There is just a warp factor h of y, which depends on a single radial coordinate within this deformed cone, deformed conifold cone. So it's a warp product of R3, 1 and this deformed conifold. Okay, now then you can actually solve for this warp factor, and it has a nice smooth form, which is monotonic and is indeed such that it attains a finite value. This is the integral form of this warp factor. And when G string M is large, you can trust the supergravity approximation. The curvature is small everywhere. So the string tension that sits at coordinate T is h to the -1/2. So since h does not blow up, you basically get a finite string tension, and we have a confining theory. I want to basically show this picture. So in a pure ADS5 cross T11 space, this h just blows up here at the minimal coordinate, and h to the -1/2, which is string tension, goes to 0. For this deformed conifold, instead of blowing up, it just stabilizes at the infrared wall, and everything is good, and the theory is confining. Now, there is another approximation to this theory, which is a kind of UV approximation. So there is log running in the UV. This is actually a solution that I discovered with Zeitlin before, the one with Strassler. It's a perfectly explicit solution, which is a kind of, it's a bit like what you would get in QCD if you just took the one loop approximation. You get the following formula. This h has a 1/r⁴ term, but it has an extra log term. And this log term is such that it screws up the metric and creates a so-called naked singularity. So the problem with this solution is exactly what is shown in this picture. So the UV behavior of the solution is same as in the deformed conifold one, but then it sort of behaves properly for a while, then it bends over, it hits a 0 here, and this is the location of the naked singularity. And in fact, this entire region, when it's non-monotonic, is already kind of sick. So the theory somehow knows how to fix this sickness. And the way it fixes the sickness is by generating the lambda QCD, very similar to how QCD fixes its one loop sickness by generating lambda QCD. So this is a solution determined from the epsilon equals 0 solution. So if you just forced epsilon to be 0, but still put in this wrapped branes, you would get this problem with the naked singularity. And this is the theory's way to tell you that you need to deform. And this epsilon is nothing but the generation of the infrared scale. So in this theory, so this is a very complicated theory. I didn't even begin to describe all the subtleties of this theory. In particular, when you study on the gauge theory side, it undergoes a so-called Seiberg duality cascade. So you have this theory like SUN cross SUN n plus m. And if you apply the duality transformation, it sort of takes you from, so you start with SUN cross SU n plus m. And one step of duality will, basically what happens is that there is logarithmic flow of couplings. One of the couplings formally diverges, and then you have to dualize it to SUN minus m. But now this theory is sort of self-similar. And then it sort of starts flowing, repeating this step. And the theory sort of starts tumbling down, down, down. And eventually it reaches, so if you start with SUKM cross SUK minus 1m, you eventually reach SU2m cross SUM, the infrared theory. So people sometimes say, so what are the facts that we see from the dual gravity? We see this dimensional transmutation in the infrared and the dynamically generated confinement scale of order epsilon to the 2/3. You also see the same pattern of symmetry breaking that you find in SUM super-Yang-Mills theory, that Z2M symmetry gets broken to Z2 by gluino condensate. I think Misha Schiffman was here. He knows a lot about this and may hopefully lecture about this in his part. But the actual theory is a little bit more complicated than this. In fact, it's best thought of in the infrared as SU2M cross SUM. And the SU2M gauge group effectively has as many colors as flavors. So you find that there are baryonic and anti-baryonic order parameters, which is like determinant of A and determinant of B operators. And what happens is that if you look carefully at the dynamics of this deformed conifold, you find out that actually there are Goldstone bosons of broken baryonic symmetry, namely this phase rotation symmetry where the baryon is rotated by a phase and the B baryon is rotated by opposite phases, actually spontaneously broken. So you find a Goldstone boson of this broken symmetry and also its massless scalar superpartner. So in fact, this is an even more interesting phase. You see confinement without a mass gap in this case. Okay, but very importantly, it's a kind of just going back to the cartoon, we basically see that in these gauge gravity duality, the fundamental string plays the role of the fundamental string in the gravity dual background describes the confining string of the original gauge theory. And you see it very explicitly here. The fundamental string does not lose its tension due to this nice plot of the warp factor. So the fact that this is non-zero and not infinity, that's confinement in the dual gravity. Any questions? Or, yeah.
The cycle that shrinks is the other one? Like you have this S2, which is...
They actually, here they shrink simultaneously. Yeah, this is sort of the mistake. So we found this solution around February 2000. It's a perfectly okay solution of the supergravity equations. I can show it again. Yeah, in this solution, the two cycles shrink at the same rate. right? Basically, there is just a overall T11 sort of shrinking together. But the deformed Conifold solution is more tricky, but it's still, yeah, I didn't have time to write out all but the form of the metric is completely explicitly known in terms of the angles. It's sort of, that's what's nice about it. You can really work with it. And
what is the difference between this one, the first one you showed?
Well, the one with Witten was just a conformal solution. So this solution, if I set M is the difference in rank, right? Like you have SUN cross SUN plus M. If I set M equals 0, then you just go back to the conformal case, right? That's just ADS5 cross T11. Okay, it's setting M equals 0. That's just a variant of ADS CFT duality with reduced supersymmetry, with just N equal 1 supersymmetry. But the problem with the solution is that it did not put in this deformation parameter. But the good news is that the theory sort of screams at you and says you forgot something, right? And what we forgot was, actually this deformation here is extremely important. This is what really breaks the infrared symmetry to Z2. We know that supersymmetric gauge theory has this solution incorporates the Gluino condensate. And if we kept epsilon equals 0, the Gluino condensate was forced to 0. So the good news is that you see, without really thinking too hard, that there is something wrong with this solution. But it's okay as a far UV approximation. So it's indeed a bit like just using one loop equations without any one loop beta function without any non-perturbative effects. Yeah, this since Misha is back. Yeah, this is, so this solution incorporates the Z2M to Z2 breaking, which he and collaborators observed in just supergluodynamics with gauge group SUM. So it has some features of just supersymmetric N equal 1 gauge theory. And this gauge theory, since obviously it's very hard to prove confinement in non-supersymmetric gluodynamics, I think just N equal 1 supersymmetric theory is another really excellent problem where we hope to get some analytic control and a lot of phenomena are known. But moreover, as I mentioned, this theory also has this baryonic symmetry breaking, and in fact, it does not have a mass gap. It has something a bit like a pion, but more tricky. Like, yeah. Well, you cannot dualize it further. Like once you reach this is the bottom. Once you reach SU2M cross SUM, and then you go on this baryonic branch. And that's sort of the cool part, but it's also very tricky. It's part of this whole knowledge assembled in the work on supersymmetric. So NF equal NC is a special case, and these A and B fields, as far as SU2M theory goes, you get exactly NF equal, you get like 2M flavors. So you get 2M flavors for SU2M, and that's why you have these baryon operators. So this is, so unlike, yes.
Another question about the cycle duality.
Mm-hmm.
This may be not even wrong. My understanding is that you start with the full theory, Km cross K minus 1M. You go down to the point where the theory starts to become sick, and then you use cyber duality to relate it to the IR of a new theory.
Yes, yeah.
so the place where I could get confused naively is type of duality. Duality between the pure IR.
Yeah. Here we're using a bit of a generalized notion about that. And actually, so Strassler wrote his own review, which is long and complicated. Yeah, this is a picture from his review. So basically, very naively, what happens is that you can say, this theory has a logarithmic flow. You can see it from NSVZ beta functions, from Novikov, Schiffman, Weinstein, Zakharov beta functions. If you apply them, you see that the two gauge couplings flow in opposite directions. There is SUN gauge coupling and SUN plus M. They flow in opposite directions. The bigger gauge group coupling formally hits a pole. And that's where you dualize it. And then you continue. So it's like a seesaw flow. It's a tumbling flow, which is sort of a more sophisticated version is shown here. It's a flow that passes near these different points, but from the field theory point of view. But in fact, like they sort of, maybe I should try to draw this. Yeah, there are two gauge couplings, right? There is G1 squared and G2 squared. Yeah. So one of them diverges here, and then they do this, and so on. So this is 1 over G squared, right? And this is 1 over, say, G2 squared. This is 1 over G1 squared. You see that here you hit a pole formally, and then you dualize. So this is, say, SU n plus M, and this is SUN. And then this gets dualized to SUN minus M. But now this is still SUN. So now this is the bigger gauge group, and it flows to strong coupling, and the history repeats itself until you tumble all the way down to this either SU2M cross SUM or SU2M plus a small number times SUM plus a small number. But the particularly simple case is without leftover brains. And this also answers a question like, why is the gravity dual reliable here? Because both couplings stay strong throughout this flow. It's sort of the magic of n=1 supersymmetric flows that you can still see using the NSVZ beta functions. You can see the logs just from even at strong coupling. So this is needless to, of course, this is some very complicated 3+1 dimensional gauge theory. As a gauge theory, it's extremely complicated. I would have no idea how to solve it or prove confinement in it or anything of the sort. But it's all somehow encoded in this equation, basically. Yes.
So the original, like, the Lagrangian of the dual gauge theory is known. That's right.
Well, it's known in the sense, yeah, it's known what it flows to in the IR, right? Because the fields have non-trivial anomalous dimensions. But it's not a perturbative Lagrangian you can use for perturbation theory. You only know it approximately near the fixed points in the same sense. Yeah, so in some sense, it doesn't describe really a fully Lagrangian theory, but schematically, we know using the n=1 supersymmetric beta functions what it's doing. But you'll have to, even though supergravity on this space takes a little work, it's completely semi-classical calculations. For example, I can do perturbations around this background and compute whole families of bound state masses. I don't just see this massless glue ball, I see whole families, and some of my graduate students in the like 15 years, 20 years ago had nice workouts computing perturbations. it's more complicated than around ADS5 cross S5. So, but this is kind of solves the theory for you and proves confinement. It's a physicist's proof of confinement, of course. But the fact that it works, I think, is nice, and it does give you this dimensional transmutation. Basically, this argument of the log R naught really needs to be replaced by this epsilon scale, and you see the infrared properties of the theory. Okay, so I think I've essentially run out of time. So I just want to add with a few comments. So I discussed basically 3 models. One is the pure glue theory and a lattice, where I think it's known what we need to prove. The numerical evidence is strong, but not perfect. It's never perfect. You're still like, I think the best simulations will have like, they still don't resolve, say, the substructure of the meson that great, for example. So there can be a lot of improvement in resolving the substructure of the confining string. But then there are the schwinger model, which comes to us from many years ago. But even there are some unclear features, like this exponentially small mass gap for the NF = 2 model at theta = pi. Then, and then this very complicated deformed Conifold theory, which somehow solves for us a theory we didn't even know existed before. It's not some theory we always dreamt of solving, right? If someone told us like, oh, there will be some duality cascade in the UV and it cascades down to, well, SU2M cross SUM is not that exotic, but still the UV behavior is highly exotic. But somehow we stumbled onto its solution, and you can say it's a physicist's proof of confinement in some exotic theory. But then there are, of course, other models we heard about at the school which have analytic control, like compact QED3, the Polakov model. These monopole instantons proliferate and they give string tension, but this theory also has some pretty exotic features which are unlike the 4D non-abelian theory. Then there is the Zyberg-Witten theory, about which we already heard, and I think Misha will talk more about it. Then from Mithat, we heard about QCD on R3 cross S1 and the semi-classics of that. So all these models have some degree of analytic control, and one can hope to build on that. But also, it would be great to find more models under analytic control or extend the range of validity of analytic control. And ongoing major improvements in the numerics have been pretty dramatic. David Gross said that it's factor of 10 to the 18 compared to the early days of lattice gauge theory, of which apparently 10 to the 9 comes just from Moore's law, and the other 10 to the 9 is just from knowing better what we're doing. I think we still need a large factor more. And one thing that's, I know very little about lattice gauge theory. I only started thinking about it a couple of years ago. But I find particularly appealing these Hamiltonian methods, which I think appeared early on in the mid-70s through the work of Kogut Susskind, although their paper was a bit sketchy in places. And then there was this application to schwinger model. As Grisha mentioned, there were some sketchy things there too. Now, almost 50 years onwards, they're still finding a little bit new things there. But it really is the preferred method for solving 1+1 dimensional gauge theories. This DMRG method or matrix product states give highly precise values. And there is no Monte Carlo fuzz, right? You just solve the finite problem. The extrapolation sometimes is extremely precise. And also these methods give connection with quantum simulators and computation. For example, there are people who have built like something like 51 called Atom Simulator for Schwinger model. And Peter Zoller's group in Innsbruck has such a simulator. And he gave a very nice set of talks at the Quantum Connection summer school in Sweden a month ago. So this Hamiltonian approach is also quantum computation in some sense, because you map it to qubits. And I think that if we can adapt it more effectively, say to 2+1 dimensions, that could change the whole sort of face of the confinement problem. So thank you very much. Thank you.
Thank you so much for a very inspiring talk. Any further questions? If no more questions, let's thank Igor again.
Thank you.